we have a topic: sustainable carbon nanomaterials, recent advances and its application in energy and environmental remediation. Carbon nanomaterials. Carbon nanomaterials represent one of the most diverse classes of material with exceptional range of properties which make them suitable for applications in widespread areas of research. There is an incisive need to look for new carbon nanostructures via sustainable and low-cost methods, realizing their role in energy and environmental application. Most of the conventional preparation strategies involve energy-intensive conditions and hence high cost of production. In this regard, green synthesis of carbon nanomaterials via cost-effective strategies derives great relevance. Natural resources, particularly biomass, waste residues like industrial effluents and plastics can generate carbon nanoparticles. Preparation of carbon nanomaterials using sustainable resources. In these we include carbon nanotubes and related structures, graphene and related structures, carbon dots and graphene quantum dots. In carbon nanotubes and related structures, we can say that CNTs can be considered as graphene sheets rolled up to form coaxial tubular structures with several micrometers length. It was first observed by Izimia S while examining carbon sample synthesized by arc discharge of graphite under TEM. Now coming to graphene and related structures, there exist several methods for the preparation of graphene such as microchemical exfoliation of graphite (CVD), catalysis assisted growth. In catalytic assisted growth of graphene, the carbon sources are used is expensive and catalysts are harder to prepare. Now coming to graphene quantum dots. Graphene quantum dots are a new class of materials that have attracted worldwide research attention in the past few years due to the exceptional spin, electronic and optical properties. Carbon dots. When the carbon nanoparticles are less than 10 nanometers, are amorphous in nature, they are called as carbon dots. They are characterized by their remarkable optical properties and fluorescence emission which make them ideal candidate for numerous applications in sensing, bioimaging and photovoltaics. Now that coming to next slide. Next slide is applications. The first application being adsorbent in water purification and gas uptake. The design of a competent adsorbent material for the separation and elimination of the industrial pollutant from wastewater is one of the major challenges in water purification. An efficient adsorbent should have fast adsorption kinetics, better selectivity and good adsorption capacity for the removal of large size molecules. A wide variety of adsorbents for the removal of organic dyes have been developed using CNTs, graphene, ordered mesophorous carbon and activated carbon. Now coming to a study, like in a study of Gong et al., PCNS derived from mixed waste particles were used as an effective adsorbent to remove MB from wastewater. The interaction between the adsorbent and the adsorbate was described by Langmuir adsorption theory. The maximum adsorption capacity was found to be 769.2 meters square per gram, which outshined other reported adsorbents like graphene, activated CNT, porous MnO2, microsphere, etc. Now coming to the second application, electrocatalysis. The use of graphene carbon nanostructures have attracted great deal of attention as catalyst supports in oxygen electroreduction reactions occurring in fuel cell. Designing cost-effective electrocatalysis is the key in developing economically and high-performance fuel cell and metal or air battery. Sevilla M employed sawdust-based graphite carbon nanostructures as electrocatalyst support for methanol oxidation reactions. The sawdust particle impregnated with Ni and Fe salts were carbonized at 900 and 1000 degrees centigrade respectively to obtain GCNs, which is graphitic carbon nanostructures. It was used as a support for making platinum electrocatalyst. It exhibited good distribution of platinum nanoparticles and the particle size were in the range of 2 to 3 nanometers. CV was used to measure the electroactive surface areas, which was found to be 90 meters square per gram of platinum, and the electrovity was estimated to be nearly 250 amperes per gram of platinum. In another interesting study, honeysuckle derived porous heteroatom doped carbon PHC with graphene-like structures showed excellent oxygen reduction reaction in 0.1 mKOH medium. The high performance may be attributed to the synergistic effect of the high ORR catalytic sites formed as a result of heterodoping. Now coming to the third application, which is in energy storage. There is an ever increasing demand to develop new renewable technologies to meet the increasing energy demands. Along with this, a robust, cost-effective energy storage is equally important. In energy storage devices, supercapacitors are superior to batteries in terms of power density, good reversibility and long cycle life. Genovese ETAL explored the electrochemical performance of biochar derived from corn cob, which is an agricultural residue, as supercapacitor electrode. The synthesis step involved a pre-treatment of the biomass species, which is nitrogen pyrolysis, and subsequent high temperature thermal chemical flash exfoliation. High oxygen functionality was exhibited by the material in the form of electrochemically active quinone and pyrone surface group. The presence of highly active surface functional group along with high specific surface area, which is 543.7 meters square per gram, resulted in an improved capacitive performance with capacitance of 221 farad per gram, which was about like 100 times greater than the natural biochar. The electrode fabricated from exfoliation biochar had no conductive additives in it, but yet it showed an excellent rate capability, holding back 75% of the low rate capacitance at a fast discharge value of 40 amperes per gram. This blend of high capacitance and fast discharge capability differentiate this material from the other high surface area activated carbon and other carbon nanomaterials such as graphene. Now we come to the conclusion and the future perspective. It gives an overview of various sustainable carbon nanostructures derived from cost-effective resources, specifically biomass and waste residues like used up polymer plastics. Special focus is on the strategies adopted for the green synthesis of material like graphene-like structures, CNTs, CDs, and various porous carbon nanostructures. It also provides an insight to some of the potential application of these materials in renewable energy and environmental remediation. The real challenge lies in developing sustainable material without causing any environmental concerns, whilst ensuring better yield and performance. Though there are a lot of conventional strategy adopted for the production of carbon nanomaterial, most of them have limitations in terms of large scale production, in addition to the use of expensive and toxic chemical. Thank you. This is the end of the PowerPoint.